Hello friends, in this lecture we will discuss about the ECG and we'll learn how to calculate rate, rhythm and axis of the ECG. So let's begin. So first is how to calculate the heart rate. Okay, how do we calculate the heart rate? So it's very easy. Heart rate we calculate per minute. Okay, so we calculate the heart rate in 1 minute. So number of heartbeat per minute will give you the heart rate. So how to calculate heart rate per minute? So there is very simple formula. Okay, so one formula is you take any two consecutive R waves. So if heart rate is regular, okay, looks like the heart rate is regular here. So you take any two consecutive R waves. Okay, you have to take any two consecutive R waves. So this R wave you calculate number of large square between these two R waves. So some consider these two. So number of large square are 1, 2, 3 and 4 large square. So formula heart rate will be equal to 300. Okay, so 300 divided by number of large square between two R waves. Okay, so 4, this will be equal to 75. So that will be the heart rate per minute. Okay, so it's very easy formula. You divided 300 by number of large square between RR, okay, or two R waves, two consecutive R waves. But this formula may be sometime a little bit inaccurate. Okay, why is it so? Because sometimes there may not be exactly 4 R waves like in this exact large boxes. Like in this ECG you can see there are 1, 2, 3, 4 and slightly more. Okay, even there is a slightly more than that. So it may be like kind of 4.25 you can say. So here how you calculate the heart rate? So ideally it should be heart rate will be equal to 300 divided by 4.25, but it becomes little bit tedious job. So what do we do here? Instead of large square we take smaller square. Okay, so how do we calculate the small squares? Okay, so in the ECG one large square is equal to 5 small square. Okay, so hence heart rate will be equal to 300 into 5, it will be 1500 divided by number of small square between two R waves. Okay, so now you need to calculate what are the number of small square between two R wave, and that will be your heart rate. So now let's assume that there are 4 large square. Just for the simplicity, there are 4 large square. So how many small squares will be there? 4 into 5, it will be 20. So 1500 divided by 20, again this will be equal to 75. Okay, this is you can calculate heart rate more accurately. If you want to calculate it more accurately, you take number of small square between two R waves. Okay, so it is given a simpler formulas. So now the question is where this 300 and 500 1500 came from. Okay, why 300? Why not we divide by 500 by large square, or why not any other number? So basically this 300 large square, it represents 60 seconds. Okay, 300 this large square, it represents 60 seconds. So why 60 second? As I already told you in previous ECG, okay, one large square is equal to 0.2 second. Okay, so one large square is equal to 0.2 second. One large square is 0.2 second. Okay, what's happening? Okay, so that's why 1 second is equal to 5 large square, and therefore 60 second is 5 into 60. Okay, see, 1 second is 5 large square, therefore 60 second will be 5 into 60, that will be equal to 300. Okay, so this 300 basically is we are calculating heart rate in 1 minute, or we are calculating heart rate in 60 seconds. That's why this 300, what this 300 represent, it represent 1 minute. Okay, so 300 large square is equal to 1500 small square. Okay, 1500 small square. That's why the 1500 small square or 300 large square, it represent 1 minute, and hence we use the number of large square between two RR and we divide 300 by that number, or we take number of small square between two RR and we divide 1500 by that number, and that's how you will get heart rate. And it's very easy by this method to get the heart rate. Sometime by just looking at the ECG you can get an idea whether the patient's heart rate is normal or not. It's very simple. I'll tell you very simple method to see to calculate what is approximate heart rate of the person. Okay, so when there is a one large square between two RR, what will be the heart rate? 300. Okay, 300 by 1. Okay, when there are two large square between two RR, what will be heart rate? 150. Okay, 300 by 2. When there are three large square between two RR, what will be heart rate? It will be 100. Okay, 300 by 100. 3. When there are four large square, the heart rate will be 75. When there are five large square, heart rate will be 60. Okay, so it's very easy. So if there are less than 3 or more than 5, it means patient either has a tachycardia or bradycardia. So just looking at the ECG, you can tell whether the heart rate is normal or not and what is the approximate heart rate. Okay, so now this is true when when the heart rate is regular. Okay, so this is true only when the heart rate is regular. What to do when the heart rate is irregular? For example, if patient has atrial fibrillation, in that case heart rate will be irregular. What does irregular heart rate mean? It means that the distance between two RR will be variable. Okay, so distance between RR will be variable. Okay, now here the distance between two RR is approximately same. There may be some variation. This is called a sinus arrhythmia, which is normal. Mild variation is fine, but when the RR is quite variable, like in case of atrial fibrillation, then it will be difficult to calculate the heart rate. Then what do we do in that condition? Okay, so I'll give you an example. For example, in the wards you have been asked to check the pulse rate of a patient. Okay, you check the pulse rate. So what you will do, ideally you should go there and check the pulse rate for 60 seconds. Okay, and you check the pulse rate for 60 seconds and it was 60 beats or per minute. That will be the pulse rate, right? But sometime because of maybe short of time or you're lazy, you might not check the pulse rate for whole 1 minute. What do you do generally? You just take the pulse rate for 30 seconds and you multiply that by 2, and that will be pulse rate per minute, right? So you check it for maybe 30 seconds and then you found there are 30 beats in 30 seconds. You multiply that by 2 and the pulse rate will be 60 beats per minute. If you are more lazy, then what you will do, you will just check pulse rate for 15 seconds and you will multiply that figure by 4. For example, in 15 seconds you heard 15 beats, you multiply that by 4 and again pulse rate will be 16 beats per minute. Okay, now you are even lazy. So here it won't matter if the pulse is irregular or irregular. You are more lazy and you just took pulse rate for 10 seconds. What is the number you will multiply to get pulse rate in 1 minute? It will be 6. So you check the pulse for 10 seconds and you found there are 10 beats. Okay, so in 10 seconds there were 10 beats, so you multiply that 10 by 6 and you will get 60 beats per minute heart rate. Now you're extremely lazy. Okay, what you do, you just check for 6 seconds. You check the pulse for 6 seconds and in 6 seconds you heard 6 beat, and what you do, you multiply which number you will need to get a 60 second. 10. 60 second is 1 minute. Okay, So here you get 60 beats per minute. So you check pulse only for 6 seconds and you multiplied that number by 10 and you got pulse rate in 1 minute. So similarly you can do that in an ECG. Okay, so here in an ECG, one QRS complex represent one heartbeat. Okay, so one QRS complex represent one heartbeat. So what you do is you take a section of 6 seconds. Okay, so this horizontal line is a timeline. Okay, so this represent time in seconds. So what you need to do is take a section of the ECG that represent 6 seconds. Okay, and then in 6 seconds you need to calculate how many QRS complex you got, or just say how many R waves you got, and if you multiply that number of R waves by 10, you will get heart rate in 1 minute. Understood? In 6 seconds you calculate heart rate and you multiply that by 10 and you will get approximate. Okay, it will not be very accurate, but you will get approximate heart rate per minute. So 6 second, how do you calculate 6 second here? So I told you that one large square is 0.2 second and 1 second is equal to 5 large square. Okay, this is important. In horizontal line, 1 second is equal to 5 large square. Okay, so 6 second will be equal to 5 into 6 is equal to 30 large square. So in a horizontal line, 30 large square will be equal to 6 seconds. So here now you will need to find out 30 large square. Okay, so suppose you started from here. Now you need to calculate 30 large square and you should do it in a single strip. Like here, this is a single strip or it is a long lead. Okay, there is no, in sometime in ECG you will find there's a broken. Like here, if you see, this is lead 1 till here, this is AVR, this is V1, this is V4. So we do not want this kind of strip. We want where there is only one single long lead. For example, if you take this is long lead 2, this is long lead AVF, so it is long lead V6. So any of this long lead you can take when you want to calculate heart rate in a irregular, when the heart rate in a patient with there is a irregular heart rate. Okay, so now we need to calculate 6 second, or we need to take 6 second, or we need to take 30 large square. So let me count one. Let's see this one. I'm not going to count, it is little fainter here. So let's see, this represent 30 large square. Okay, you calculate carefully in ECG. Suppose this much is a 30 large square, it means this is a strip that represents 6 seconds. Now you see how many R waves are there. 1 2 3 4 5 6 7 8 9 10 11 12 13. So there are 13 large square, oh sorry, 13 R waves, means 13 beats. Okay, one QRS is 1 beat, so there are 13 beats or 13 R wave, and that is in 6 seconds. Okay, in 6 seconds you got 13. So how many R wave will there in 60 seconds? You multiply that by 10, so it will be 130. Okay, 130. So that is a heart rate here. So what is the heart rate? 130 beats per minute. This is, you can calculate the heart rate in a patient where the heart rate is irregular. Okay, or the rhythm is irregular. So these are the method to calculate the rate. Okay, now let us see how do we calculate the or look for the rhythm of the heart. Most of the time the rhythm will be regular. What does that mean, regular rhythm? It means the interval between two RR is almost the same. Okay, if the interval between two RR is the same, you can say the rhythm is regular. But sometime the interval between two RR will change. In that condition you will say it is irregular. Okay, rhythm is irregular. So how do you calculate how do you look for whether the rhythm is regular or not? You need a compass. Okay, and you can just look, you can just coincide the two tips of this compass with these two R waves. Okay, and you go to some other point and you try to coincide. Okay, or what you can do is you take a strip of paper. Okay, you take a strip of paper like this. Okay, suppose this is a strip of paper, and you try to match it with the you try to put it just like here where there are tips of R wave, and you mark it. I'm marking the strip of paper. Here I made a mark with the pen, here I made a mark with the pen, and here I made a mark with the pen. Now what you do, you lift this paper and you go to some other point and you try to coincide. This is the mark you already had made, okay, and you try to coincide these marks with this tip of R waves. If they coincide well, there may be slight difference, that's fine. If they coincide well, you can say heart rate is regular, okay, but sometime they may not coincide. Like for example, I took a paper here and I put it at the tip of R wave, then I made a mark with the pen here, okay. Now I lifted this and I try to put it here. This paper I try to put it here. So here is one mark, I will try to coincide. Second mark was here, and the third was here. Is it coinciding now? No. Okay, it means the R wave are not coming at a fixed interval, they are variable. That's why it is a irregular heart rate. Okay, so heart rate here is a irregular. Or just by looking at the ECG, you can count the number of large square between the R waves. See here there are only 2 large square, but here there are, looks like there are more than 3 or 4 large square. So it means the heart rate is irregular. This is how you can calculate whether the heart rate is regular or not. Now third section, how do we calculate the axis, okay, or how do we look for axis. So before looking at the axis, we have to understand what is the axis of the heart. Okay, what is it? So basically axis represent, it is the resultant direction of the flow of electrical activity in the heart. Resultant direction, okay, or average in what direction the current is flowing in the heart, that is the axis. In previous videos I told you that current is a vector quantity, okay, current is a vector quantity. What does it mean by vector? It has a magnitude as well as direction, okay, little bit of physics. There are scalar quantities which just has a magnitude, for example speed, okay, and there are vector quantities which has magnitude as well as direction, example velocity, okay, it has a magnitude as well as direction. So the current here is a vector quantity, it means it has a magnitude as well as direction. And when you want to calculate the resultant, you need to add them, okay, you need to add all the different current which is flowing in the heart, okay. Suppose this is a heart, here is a SA node, here is a AV node, okay, then there is a bundle of his right and left bundle Purkinje fiber, and there is a first atrial depolarization, then ventricular. So current flows in various directions here, the current flow in various directions. So what you need to do is you add up all this current and you try to find out one single direction and one single magnitude, okay. Just for your curiosity, I will tell you how we add the vector quantities, okay. Suppose this is a one vector, okay, its magnitude is maybe this much, maybe 1 or something, and there is another vector, its magnitude is 1, and this is the direction. And how do you add these? What you do is you lift this vector from here and you put it here. The tip of this will coincide with the end of this one, okay, and then you join a line from this point to this point. Sorry, it should be okay. So this will be the resultant vector and that will be the direction of the resultant vector, okay. This is how vector quantities are added. So what you do is you add all the current in the heart, so and you will get a resultant vector and a resultant direction. That direction will be called as the axis of the heart. We need to plot it on a graph paper, okay. We need to plot that axis on a graph paper and you can tell exactly what is the axis of the heart, okay. Suppose this is x-axis, this is y-axis, okay. this is 0, this is plus 90. I'll draw a different point. Okay, let me draw here. Okay, so this is x-axis. I think I taught you this in the previous lectures. So this is x-axis, y-axis, this is 0, this is plus 90. Okay, this is minus 90, this is minus 180. I told you it's a little bit different from the usual graph paper. Okay, usually the upper part is positive while the lower down is negative, but here the lower part is positive while the upper part of this x-axis is negative. Okay, and the axis, if you plot this axis, it generally varies from minus 30 to plus 90. Okay, if the axis of the heart falls in between this, you can say it's a normal. Here heart is at the center. Okay, heart is at the center, and you calculated the resultant direction of the flow of current in the heart. This is 0 0. So suppose this is a direction of resultant current, and you measure it is maybe around 45 degree. So this angle is 45 degree, and this is the direction. Then you say this is the axis of the heart. Okay, what does it mean? It means the current which is flowing in the heart is flowing, the average direction of this current is this one. Okay, so generally the average direction lies somewhere between minus 30 to plus 90, but in some condition, for example, you just take a condition where there is a left ventricular hypertrophy. Okay, so there is a left ventricular hypertrophy. This is a ventricle, and patient has a hypertension, and because of that patient developed left ventricular hypertrophy. So the wall of left ventricle have thickened. Okay, so what will happen here? More current will flow toward left. Okay, more current will flow toward left, and hence the axis of the heart will be more toward left. Okay, so sometime it may be less than minus 30. The axis may go less than minus 30. That condition will be called as left axis deviation. Okay, if suppose there is a right ventricular hypertrophy, more current will flow towards right, and the axis of the heart may be deviated towards right. It will be more than plus 90. That will be a right axis deviation. Okay, so in the ECG you will find there is a left axis deviation or there is a right axis deviation, and then you have to make some conclusion. If there is a left axis deviation, you think if the patient has left ventricular hypertrophy. Okay, or there is another condition that causes left ventricular left axis deviation. It is something called as left anterior hemiblock, where there is a block of anterior fascicle. Okay, or in left bundle branch block you will get left axis deviation. Okay, so look at the left axis and think of if there is any such kind of blocks, or if there is any left ventricular hypertrophy. If there is a right ventricular hypertrophy, think of if there is if there is a right axis deviation, you have to think whether the patient has a right ventricular hypertrophy or whether the patient has a left posterior hemiblock. In that condition, the axis will be deviated toward right. So how to calculate this axis? Okay, so I'll tell you there are three methods. One is the simplest and the least accurate. There is one simplest, but it is least accurate. Okay, I generally use this method only. Second is little bit difficult, but it is more accurate. You can skip on this. And the third is more difficult and it takes time, but it's very precise. So I'll tell you the first and the last. You can forget about the middle one. So first, which is the simplest method. In this method, you take two leads which are perpendicular to each other. So you have to see that lecture on the leads. Okay, so what are the leads which are perpendicular to each other in a ECG? The lead 1 and lead AVF. Okay, in 0 degree there is a lead 1 and at 90 degree lead AVF. So you just, these two leads, they are perpendicular to each other. Okay, so you just take these two leads. Okay, and you have to see the direction of resultant deflection in QRS. Okay, what did I say? Direction of resultant deflection in these two leads. Okay, lead 1 and AVF. So sorry, direction of resultant deflection of QRS. Okay, so how do you calculate this resultant deflection of the QRS? In all the lead, this QRS complex may not be present. Okay, it is generally Q and R, or it may be R and S. So how do you calculate the resultant deflection? Resultant deflection can be positive or it can be negative. Okay, so here just take an example. Suppose it is 3 negative, there is a Q wave which is 3 small square negative and 10 small square positive. Okay, so you just count the number of small square here and here. So 3 mm and it is 10 mm. So what will be the resultant deflection? You need not convert it to the millivolt. So what will be the resultant deflection? It is 7 mm positive. Okay, take another condition. This is a Q wave, this is a R wave. Okay, here it is 10 mm negative, 3 mm positive. What is the negative deflection? Negative 7 mm. Okay, so this is how you calculate the resultant deflection. So here in when you are let's see in ECG example. So sorry, here you see what is the resultant deflection. Okay, you try to calculate. You have to check lead 1 and lead AVF. Okay, lead 1, I'm not very sure, the baseline is little bit hazier, so I cannot properly calculate here, but let's see. There is a very small Q wave which is not visible. Let's say it is 1 mm, just for sake of it, just say it is 1 mm. 1 mm negative, and how many millimeter positive? 5, and this is around 4 9, and this one here 10. Okay, so here 1 mm negative and 10 mm positive. So what is the resultant deflection? Positive 9. Okay, or you can say resultant deflection is just positive. Okay, and in AVM you see what is the resultant deflection. It again look positive. You need not measure it, but it is positive. Okay, so keeping this information in mind, we can just calculate the axis of the heart roughly. Okay, not very accurately, but roughly. I'll tell you how to do that. So you just check lead 1 and you take lead AVF. In some books they advise to take lead T3, but I always take lead AVF. And in case of normal axis, the resultant deflection will be positive in lead 1 and it will be positive in lead AVF. Okay, positive in lead 1, positive in AVF. So just by looking at the ECG you can say, oh, it is a normal axis. Okay, now in case of left axis deviation, what happens? The resultant deflection is positive in 1 and while it is negative in lead AVF. They are kind of leaving each other. L for leaving. Okay, they are leaving each other. One is going up, AVF is going down. So this positive deflection, they are leaving each other. It means it is a left axis deviation. While in RAD, the deflection in 1 will be negative and AVF will be positive. They are kind of reaching each other. They are reaching each other. They are coming towards each other. That is a right axis deviation. Understood? So let's see by example. Okay, here in lead 1, what is the resultant deflection? Positive. In lead AVF, what is the resultant deflection? Negative. They are kind of leaving each other. That's why this ECG is showing left axis deviation. Okay, another example. Here in lead 1 the resultant deflection is negative. In AVF the resultant deflection is positive. So they are reaching each other. So this is a right axis deviation. Okay, this is a left axis deviation. Okay, so this is one method to calculate axis of the heart just by looking at the ECG. It is simplest method and it works in most of the time. Okay, all right. Then there's another method which is more accurate, and let's try and understand this more accurate method. So again, but for there you need a graph paper and you need to plot the ECG on that graph paper. Okay, you need to actually plot the current in that graph paper, or you need to plot the resultant deflection in that graph paper. Okay, so you must have seen a graph paper when you were at school. So this is lead 1. Okay, and this is lead AVF. This is obviously x-axis and this is y-axis. The values here, they are positive. This one are also positive. The values here are negative. Okay, so these are the positive values, these are negative, these are the negative, and these are the positive. Then you calculate the resultant deflection in lead 1. I told you how to calculate. Okay, so you calculate the resultant deflection in lead 1. Now for example, in lead 1 the resultant deflection was 7. Okay, so you calculate 7, 1, 2, 3, 4, 5, 6, 7. Here is the 7. You mark this point. Okay, in lead 1 the resultant deflection was 7. This was the lead 1 looked like. 3 negative, 10 positive. So resultant deflection was 7. Now you come to lead AVF and you try and calculate the resultant deflection, and it was again 7. 1, 2, 3, 4, 5, 6, 7. So you mark this point. Okay, it can be anything, it may be 10. For simplicity I'm just assuming it is 7. Okay, so maybe 4 negative and 11 positive. Okay, so this is 4 negative Q wave and 11 positive, so it comes 7. So you have this point. Then you draw a perpendicular from this point and one perpendicular from this point. Okay, and they will meet here. You will get this intersection point. This point will be labeled as 7 and 7, but anyway you need to focus on this point, and here is one point at the center, 0, 0. Okay, you draw a straight line meeting these 2 points. Okay, kind of this. That is the axis of your heart. If you measure this angle from 0, it will be 45 degrees. Okay, because it is equidistance. It can be anything. You need to measure with that instrument which is used to measure the angles. Okay, but approximately you can say. So the axis of the heart is 45 degree, and it is, I told you, normal axis is minus 30 to plus 90. So this value lies in between the values, in between this. That's why it is a normal axis. Okay, now let us consider a condition where there is a left axis deviation. Okay, you plot a graph paper like this. Okay, and let's see what happens in left axis deviation. In lead 1 it is positive, right? In lead 1 the deflection is positive. Suppose the deflection is here somewhere, 5 mm resultant deflection, while in lead AVF it is negative, so it will be plotted above the baseline. Got it? In lead AVF, see, the resultant deflection is negative. It is above, below the baseline, right? So when it is negative, you have to plot on the upper part of the axis. So you have to plot it here. I told you this one is negative, okay, not like normal graph paper. In heart, the graph paper we use is little different, okay. So this is one value you got, and suppose it is again 5 negative, this is another point you got. You take a perpendicular from here and one here, and it is the point where these two meeting. This is -5 -5. You join these two line and you draw this line, okay. So it is around -45 degrees, okay. So it is less than -30, it means there is a left axis deviation, okay. When the axis is less than -30, it becomes left axis deviation, okay. Now similarly, in case of right axis deviation, what happens? In lead 1 it is negative, okay. In lead 1 it is negative, and lead AVF it is positive. So one perpendicular like that, one like that. Oh, sorry. So you got this point and you need to join these two, and it is more than +90, so it will be a right axis deviation, okay. And just have a look here. Here you can see lead 1 it is negative, okay. So if you draw like that, lead 1 it is negative, so you will plot it here. Lead AVF, the deflection is positive, so you will plot it here somewhere, okay. You got this point, you got this point, you draw perpendicular, you get this intersection point, you draw a line like this, and you measure. So definitely it is more than 90. So when it is more than 90, when the axis is more than 90, it is a right axis deviation, okay. So this is how you can calculate the axis, okay. So now what you can do is you read about the causes of left axis deviation and the right axis, okay. I will stop here. Thank you very much.